This is the bondage of radius 2 kilometers. Radius 2, yes, it's common. So Dr. anything on exams today too?
No, I'll grade by Wednesday.
Good, I'm not in the mood. I'm not in the mood to get.
All right.
They'll be online tomorrow?
Wait, what?
Do you think they'll maybe be online tomorrow?
If I finish them by tomorrow, I hope to finish them by tomorrow evening. So yeah, they should be online tomorrow. What?
Did you start?
I graded like 5 of them.
How was it?
Pretty good so far. I think no one scored lower than a 43 so far out of 50. But that, I mean, that's only 5. But you know, so far they look good though. Yeah. Hey, how's it going? See you guys. See you tomorrow.
Will you teach 441 next semester?
441. I'm not sure. Is it listed online? Okay. Yeah. Usually they decide the technical elective. So everything that's like 400s, that's not a required class for undergraduates. They call it technical elective, and so they don't list those until the summer usually. Because what the department does, he checks and see who's available in terms of our part-time faculty, because they end up teaching a lot of those classes too. And so if he needs it, then he'll ask me to teach it. Yeah, but I requested it, and so I'm hoping it's being done.
I'm thinking of doing that course.
Okay, yeah, no, it's a good course. Yeah, I taught it for the first time just last semester. I'm probably going to make some pretty big changes to it, but you know, it's a good course.
Yeah.
Yeah. Mhm.
much is it? 170, you said? You said you can't.
All right, it's 7 o'clock, so let's go ahead and get started. All right, good evening, everyone. How's everyone doing today? Good, good. All right, so last time I saw you guys, we were taking the midterm, and so so those midterms aren't yours; those are for another class. And so I haven't finished grading your guys's. I was hoping to have more done by today, but some stuff came up this afternoon, and I couldn't work on it. So I've graded about 5 of them, and so far they look pretty good. But you know, we'll see how it turns out, kind of, you know, once I finish them. But I do plan on finishing them by Wednesday. You know, hopefully by tomorrow evening, so you guys will know what you got on the exam. Okay, and so before we get started today, I do want to kind of show you our roadmap for the rest of the semester, right? And so we have 2 weeks left, and so we have this week and next week. That means we have 4 more lecture sessions, right? So this lecture notes that I'm going through right now, this is the last lecture notes that I plan on going through this class. It's probably the most essential one that you need for your projects, and so it's a good one to do. Okay, and so I anticipate we'll probably spend today and on Wednesday finishing it up, right? Just because I want to go through the algorithm today, and there's a very lengthy example that I want to go through. Just kind of showing you this whole process. Okay. And then next week, we have Monday and Wednesday next week. I plan to just reserve those days just to work on the project. Okay? And so what I mean by that is, I'm not going to be lecturing anything on those days, but I will be going around helping you guys with your projects. Okay, and so to make the most of those days, it would help if you kind of get rolling on the project. Start doing some coding. Maybe hit a wall, and then once you hit a wall, then we can talk about it next week, and we can kind of work through those problems in class together. Okay. I like this just because I know just because you guys are graduate students and a lot of you are working, so it's hard for you to find time to come to office hours, and so I wanted to save some class time just for me to kind of give you some feedback on your projects to just to make sure you're all kind of on the right foot, because everyone at one point or another, usually on this project, usually you probably need some help or some guidance or some feedback from me, if not from me, from maybe one of your friends or peers from the class. And so I think the class times are perfect to do that, because we're all, I mean most of you are virtual today, but typically we're all here in class together, and I'm here as well, and so I think that's the perfect time to work on the projects. Okay. And so for next week, you're definitely, of course, you're welcome to keep continuing. You're welcome to attend virtually. And actually, you're welcome to not attend at all, because I'm your instructor, I'm not your mom, and so I can't make you come to class. But I will say that generally speaking, for these kind of workshop days, the people that come in person it's a little bit easier for me to get to them, just because I can physically see them in the class. And typically, what I'm doing is I'm kind of going around the class, and as people raise their hand, I kind of go to them. I try to make my way back to the podium every now and then to catch some Zoom questions, but it usually isn't as often. And so if you want to kind of make the most out of the sessions, then I would recommend coming in person. But of course, I'm going to try my best to work on Zoom. And if those next week doesn't work out, or if you need to work on other stuff, I know you guys are really busy too. We can of course always set up some private sessions as well. So we can I can open up my Zoom room, or you can come into my office. Whatever kind of works best for you to get help on the project. Okay, but I want to make sure that we have all the time and you have all the support you need to get the project done, because it's a lot of coding, and I know quite a few of you have already started, and I've already talked to some of you already, but it is quite a lot to do. And so especially as we're going through the algorithm today and Wednesday, I know a lot of you are going to start applying it, especially because we're done with the midterm now, and so I want to make sure you guys are all on getting off on the right foot. Okay. Another thing I wanted to mention is that originally I had planned to have one more homework assignment due at the end of the semester, but I decided to kind of skip it. And so because I want you guys to just focus on the project. And so I know if there's a homework assignment out there, then you guys can be working on kind of both at the same time, but I want you guys just to focus on the project from there. Okay. But I will say that there's one critical component of the final homework, which was the coding problem. If you remember from many weeks ago, when we did that kind of 1D finite element example, right? I did post a solutions to that, right? And I think what's key for that one is that that code there has an example of how to do 1D Gauss Quadrature in MATLAB, right? And so I definitely recommend checking that out, just so that you can see how that's implemented in MATLAB, and that might help you out for the final project as well. Okay. Question. So you have set up office hours. Are you okay with any day like Tuesday, Thursday, or Friday, like flexible resume for fun? Yeah, of course. Yeah. I mean, if you can't make my regular office hours time, then you could definitely set up an appointment on any of those days. Yeah. So just send me an email. I mean, of course, I'm not, I have meetings and stuff like that. And so, but if you send me an email a few days in advance, then we can schedule something where, we can have a session over Zoom, of course. Yeah. Okay. Okay, and so I think that's all my announcements. And so, hopefully that makes things clear for the rest of the semester. So are there any questions I can answer before we get started? Okay, all right, so let's go ahead and get started. And today, our question, you can send me the code to ask you to take a look. Yeah, of course. Yeah, you can, I'm always happy to take a look at code. It's always easier for us to look at code together. And so if you can send me your code and we can talk about it in an appointment, that's always the easiest for me. If you can't make time for an appointment, you can send me your code and I can send you my feedback over email as well. Okay. Okay, so last time we left off, last Monday, we had just got done talking about, how to apply the isoparametric concept, okay, isoparametric approach. Okay. And so just to kind of remind you, the general idea is to take, an arbitrary element, okay, right? And so this might be an element that's produced in physical space. Okay. And so this might be an element that's produced by a general measure, so produced by ANSYS, or for the case for your guys' projects, produced by MATLAB, okay? And so usually when those meshes are created, they kind of distort the elements as they need to fill the space, okay? But the problem is, if we want to do computations on these generic elements, they're difficult to do because, these elements are kind of arbitrarily oriented, okay? And so what we want to do is we want to take this element, we want to map it to a template element, okay? So this element has the exact same size and exact same shape, okay? Okay, so sometimes we call this the parent domain. Sometimes you can call it the isoparametric domain, okay? But the point is that these elements here have the same shape, okay? And with the change in coordinates, we change the variables to epsilon and eta instead of x and y, okay? And so we call this node 1, 2, 3, 4, okay? And the benefit of this is that, once we're in this domain, we can compute our element stiffness matrices and element forcing vectors a lot more easily. Okay. Okay. Right. Of course, that's debatable, right? And so, with all the steps that we have to take to get to the isoparametric concept, it's there's definitely a lot of steps involved, and so you're free to have your own opinions on whether it's easy or not. But what is true is that if we do the computations in this domain, it lends itself to a computer algorithm a lot more easily, and so it's a lot easier to code the method, by using this concept. Okay. All right, and so today we're actually going to apply it. And so we spent kind of the last maybe 2 or 3 lectures talking about all the different steps, but we haven't put it all together yet. And so today we're going to put it all together into a single algorithm, okay? And I've written this algorithm in such a way that you can apply it kind of directly to your code, okay? And then after we talk about the algorithm, we're going to apply it to an example, a fairly lengthy example, just so you can see how it all works out by hand. Just so that you kind of know what's going on as well. Okay, so this algorithm here, I think, is kind of one of the most important things, especially for your project. Okay, and so we're going to be applying this to a 4-node quadrilateral. Okay, which is exactly what's shown above. Okay. And since we're going to be using Gauss Quadrature to perform the integration, we have to choose a Gauss Quadrature scheme, okay? And so we're going to use a 4-point Gauss quadrature for this element. Okay. Okay. So let me go ahead and draw quadrilateral here. Okay. I kind of misdrew it. It's a square, you know. So I drew it kind of like as a rectangle, but it's actually a square. Okay. But this makes it a little bit easier for me to draw. Okay. And so there's our 4-node quad, right? And so since this is in a parent domain, if we list out the coordinates of our corner nodes, we have -1, -1, 1, -1, 1, 1, and oops, and -1, 1. Okay, so those are the corner nodes. But in order to apply Gauss quadrature, we're going to integrate this or evaluate it at the Gauss points. Okay, and so the Gauss points are approximately in these locations. Okay, right. So where this Gauss point right here is -1 over √3, comma -1 over √3. Okay. This one right here is 1 over √3, comma -1 over √3. Okay. This one right here is 1 over √3, comma 1 over √3. And this last one right here is -1 over √3, 1 over √3. Okay. Okay. And so in green there, that's the Gauss points. Okay. All right, and so what we're interested in is that for this element, okay, assuming that it came from a physical element of an arbitrary shape, just like above here, okay. Okay. And so let's say that this element looks something like this. Okay. And so I'm drawing it again just so I can label some of the points. Okay. I know I kind of drew it up there. Okay. Okay. And so since this element is coming from physical space, then each of the nodes are going to have their physical coordinates, right? And so the bottom left, we're going to say is x1, y1. Okay. There's going to be x2, y2, x3, y3, and then x4, y4, okay? Right, and so assuming that this element up here came from this one down here, right? And so we perform basically this change of coordinates, right? What we're interested in computing right? And so what this algorithm is going to do is going to allow us to compute the element stiffness matrix and element forcing vector for this arbitrary element right here. Okay. All right. So does the problem kind of make sense? And so we have this arbitrary, we're starting, maybe I should have started here, right? And so we're starting with this arbitrary element here in physical space. We have the XY coordinates of all the nodes, okay? We're going to perform the transformation into the parent domain, okay? And use that parent domain to evaluate the element stiffness matrix and element forcing vector, okay? And so at the end of this, you're going to have a single element stiffness matrix, so KE, as well as the element forcing vector FE for this element. Okay, but to get there, we have to go through the isoparametric approach. So we have to go through the parent domain, compute everything, and then and then that's going to give us what we want. Okay. Any questions on this so far? Okay. All right. So let's look at the algorithm. Okay. And so the algorithm is written in terms of an algorithm. Okay. And so the algorithm kind of starts like this. All right. Okay, so we start with the for loop, okay? Okay. And so what we say is that for each Gauss point, okay, so we're going to repeat everything in this algorithm for each Gauss point, okay? And so, if we go back to our parent domain, right, we have 4 Gauss points here. And so we have, those are all the 1/√3s, right? And so we're going to start with maybe this one, okay? We're going to start with the one in the bottom left. We're going to run through our algorithm, compute everything we need to. Then we're going to move on to the next Gauss point. Okay, we're going to do everything we need to. Okay, save it, and then come back and then do the same thing for the third Gauss point. Do everything we need to, save it, and then do it finally for the fourth one. Okay. And so when I write the algorithm like this, it's generic. And so say if you want to change the Gauss scheme to maybe like a 1 point, or maybe to an even greater one, like a 9 point, then this algorithm can kind of adapt to that. But for all intents and purposes, for now, since we're focusing directly on the 4-point rule, okay, this means that this is going to loop 4 times. Okay. Okay. And so for this case, this loop is going to loop 4 times. So we have 4 Gauss points, right? And for your projects, I believe we use a 3-point Gauss rule, and so you're going to loop 3 times. Okay. Okay. And so we're going to do this, everything here for each Gauss point. Okay. Step 1. Step 1 is to establish the parametric coordinates for this Gauss point. Okay. Okay. And so that means establishing what? Epsilon G, I call it epsilon G. Okay. And eta G R. Okay. And so this is going to change every single iteration of the loop, right? And so for instance, if we're doing this for the first iteration, right? And so we're doing the bottom left Gauss point, epsilon G here is going to be minus 1/√3. And eta G is going to be minus 1/√3. Okay. That might be an example for the first loop, but for the second loop, right? For the second iteration of the loop, then epsilon G might change to positive 1/√3. Okay. And so in other words, you have to establish what these are. Okay. All right. Step 2. Step 2. Now that we know the values for epsilon and eta at the Gauss point, then we can compute the values of the shape function at that point. Okay. Okay. And so remember, we have 4 of them, right? So we have N1, N2, N3, N4, right? And so we have N1 here of epsilon G, eta G, Okay. And same thing for N2, N3, and N4. And so for a 4-node quadrilateral, our shape functions look like the following. And so we have a 1/4. Okay, for N1, we have 1/4, 1 minus epsilon g, 1 minus eta g. Okay. N2 is 1/4. It's on the next page. 1 plus epsilon g, 1 minus eta g. Okay. N3 is a plus plus, and so 1 plus epsilon g, 1 plus eta g. N4 is 1 minus epsilon g, 1 plus eta g. Okay. Right. And so you should get numerical values for all of these because epsilon g and eta g are defined, right? They're fixed at a certain Gauss point. And so each of these functions here should return to you a value, right? And so you should have four numbers from this, okay? And so, the next step, this step here is just evaluating the shape functions. And, we're going to use that in a lot of different ways. 3. All right. Step 3 here is to, now that you have the shape function values, we can also compute the shape function derivatives at the Gauss point. Okay. All right, and so we have 8 of these, and so there are a lot of them. Okay. So I'm going to write them all out just for completeness because this is an algorithm. Okay. And so just so that you can kind of use this in your code. Okay. Well, you can't use this for your project because your project has triangles. This has quadrilaterals, but it'll be helpful for the example we do later. Okay. All right. So first we have partial n1 partial epsilon, and so that's -1/4 times 1 minus eta g. Okay, then we partial n2 partial epsilon, so this is 1/4, 1 minus eta g. Okay. Then we have partial n3 partial epsilon, and so this is a positive 1/4, 1 plus eta g. And partial n4 partial epsilon, so this is a -1/4, 1 plus eta g. Okay. And then we have the same things for the eta derivatives. Okay. Right, so for a four-node quadrilateral, those are all the shape function derivatives. Okay, so we're going to need all 8 of them because we're going to use them to compute things like Jacobians and whatnot. Okay, and this is an official part. This is not an official part of the algorithm, at least not in the notes. But it's almost a necessary step because because of how we're going to use it next. It'd be good to kind of save this into a matrix. Okay. And in fact, it'll be useful to save them as two matrices. Okay. And so we can save one as a 2x4 matrix, okay, kind of in the same format that you see above. Okay. Okay. Where the first row of that matrix is all of the derivatives with respect to eta, and the second row of that matrix, or excuse me, so the first row of the matrix is all the derivatives with respect to epsilon, and the second row of the matrix is all the derivatives with respect to eta. Okay. And of course, the other form of this matrix that'll be useful is its transpose. Okay, and so the transpose of this is going to be 4/2, where you just simply take the previous matrix and just transpose it. Okay, and so MATLAB has a useful function to transpose matrices, and so you can just go ahead and do that. Okay, okay? And so it's going to make the maybe not the next step, but the steps after that a lot more easy. I suppose you can do that for step 2 as well. Okay, so step 2, you can make that into a matrices too. Okay. All right. And so I know this is a lot of equations, but again, this is meant to be a computer algorithm, right? So each equation here is just kind of another line of code. You can just kind of code that into your MATLAB. Okay. Any questions on any of this so far? Okay. All right, so now let's go on to step 4. You zoom in back again. Okay. Step 4 here is that we want to compute the physical coordinates of the Gauss point. Okay. In other words, this is what we're going to compute. And so we're going to compute x of epsilon g, eta g, and y of epsilon g, comma, eta g. Okay. Okay. You'll see me refer to these just as xg and yg, just for short. Okay. All right. So remember, when we did Gauss Quadrature, for your exam or for the previous homework, right? There was a point where we plugged in for x and y in our integrand, right? And so before we could do Gauss Quadrature, we had to plug in for x and y, right? So this is kind of what we're doing here. And intuitively, you can think of it like this, right? Because we're performing this mapping between these two nodes or these two representations, right? And so if we're evaluating everything at this location right here, so let's say that we're doing the first Gauss point, okay? That also has a corresponding location in physical space, right? And so that's maybe somewhere right there, right? And so in order for us to perform our Gauss Quadrature, we need to know what that location is, okay? And so that's what we're going to do here. And so basically the way that we do this is we just plug in epsilon g, eta g into our coordinate transformation, right? And so if you recall, so our function epsilon g, eta g, okay, this is going to be equal to the dot product between all the x coordinates of our physical element for the corner nodes and the corresponding shape functions, right? So we have x1 and 1, epsilon g, eta g, okay, plus x2 and 2, epsilon g a to g plus x3 and 3 epsilon g a to g plus x4 and 4 epsilon g a to g. Okay. Right. And so this is where step 1 or step 2 comes in clutch, because all these n1s, n2, n3, and 4, we've already computed these, and so all we have to do is just multiply them by the physical coordinates of the original node. Okay, and you'll have that information too, and so you'll have that information available to you because you're going to know where all the corner nodes lie. Okay, and then same thing for y. Okay. And so that's going to give us xg and yg. Okay. And so after step 2, this is just kind of pretty easy, right? So you just take the x and y coordinates of the original node and you just kind of plug them into this expression right here. Okay. All right. So that's step 4. Step 5 is to compute all the Jacobian rated quantities. And so we need to compute the Jacobian itself. We need to compute the determinant of the Jacobian, as well as the inverse of the Jacobian. Okay. All right. And so the easiest way to do this is through matrix multiplication, right? So remember in step 3, right? After we computed all the shape function derivatives, I told you to save it as a matrix. Okay. And so this is where it's going to come in clutch, right? And so remember the Jacobian is defined as this 2 by 2 matrix. And so we have partial x, partial epsilon, partial y, partial epsilon, partial x, partial eta, partial y, partial eta. Okay. And so we can compute these using this matrix multiplication. And so first, we have our shape function derivatives. And so this is the 2 by 4 version. And so this is going to be partial n1, partial epsilon, partial n2, partial epsilon, partial n3, partial epsilon, partial n4, partial epsilon. Okay. Partial n1, partial eta, partial n2, partial eta, partial n3, partial eta, partial n4, partial eta. Okay. And then to compute the Jacobian, we multiply this by 4 by 2, where the 4 by 2 is just all of the physical coordinates of the physical space node. Okay. So we have x1, y1, x2, y2, x3, y3, x4, y4. Okay. All right, and so if you save your results from step 3 into the 2 by 4 matrix, okay, and then you have the physical coordinates, and I suppose it's useful at this point to store the physical coordinates as a 4 by 2 matrix. Okay, then this ends up being pretty easy. Okay. Okay. All right, and so in MATLAB, this just ends up being a matrix multiplication. Okay, and once you have this computed, you can just take the determinant of the matrix. Okay, there's a MATLAB function to compute determinants, and so that's a very simple thing to do. Okay, And there's also a MATLAB function to compute the inverse of a matrix as well. Okay, so once you perform this matrix multiplication, then computing the determinant and computing the inverse is just a matter of calling the appropriate MATLAB function. Okay. Okay. All right. Any questions on any of this so far? Okay. I know it's pretty dry at this point, but once we do the example with hand calculations, hopefully it'll put some give some context for all these things. Okay. All right, step 6. And so step 6 is to compute the shape function derivatives in the physical space. Okay. And so if you recall, these physical space shape function derivatives are needed for the element stiffness matrix. Okay, remember that traditionally the element stiffness matrix has derivatives in the physical space, so that's x and y. But right now we don't have that. We only have the shape function derivatives in the parametric space, in the parent space. Okay, and so we need to perform some operations in order to get these. But luckily, we already have most of the things computed already in terms of what we need. Again, it's just gonna end up being a matrix multiplication. Okay, so let me show you the version that's going to fit here. Okay. And so if we define the physical space shape function derivatives as this matrix, okay. And so we have partial n1, partial x, partial n2, partial x, partial n3, partial x, partial n4, partial x. Okay. Okay. So those are all the shape function derivatives that we seek. Okay. And so what we say is that this is equal to all of our shape function derivatives in the parametric space. Okay. Okay. Remember, we computed these in step 3 and we saved them into a matrix, right? Right. Okay. And then what we're going to do from there is we're going to multiply it by the Jacobian inverse. Okay. Or, so I did that version first just because it's easier to fit. But I think the one that I have in the notes and the one that's implemented in most of the code is kind of the transpose version of this. Okay, and so what we have here, I did the above to avoid writing this, but I think I should write this version down too because it's the more traditional one. Okay, and so the more traditional one is just everything kind of transposed with each other. Right? So we have partial n1, partial x, partial n2, partial x. And so I'm just repeating the same shape function derivative matrix in physical space, but I just transpose it, right? So now it's 2 by 4. Hang on. Sorry about that. Okay. So all I did was I just transposed just the whole system. Okay. So they should be equal to each other, but just for the sake of consistency, both in your codes and in the example, let's go with the second version because that's what's in the textbook. That's what's in my book. Okay. So once again, this task, I think we spent almost half the lecture last Monday talking about this, but with just kind of how we set things up so far with the matrices that we saved and what we've computed, this is just kind of a one-line. It's actually just a one-line piece of code, right? And so we have the Jacobian inverse. We have that already. We have that from step 5, and we have the shape function derivatives in the parent space. We computed that in step 3, and so it's just kind of putting those two together and multiplying them, and then we automatically have our shape functions in the physical shape function derivatives in the physical space. Okay. And just so I don't have to keep writing this entire thing right here, I'm gonna call this matrix BG. Okay. Okay. And so that's our primary ingredient for the element stiffness matrix, and so that's pretty key for us. Okay. Okay. So we're almost done. And so, the other thing that we have to compute for the element forcing vector is the thermal generation term or the source term. Okay. And so we have to compute its value at the Gauss point. Okay. Okay. All right, so we'll call this S sub G, okay? Because normally we have the function S of X and Y. Okay. And then all you're going to do is that whatever functional form your S function is going to take, you're going to plug in X sub G and Y sub G. Okay, so I believe we computed that in what step 4, I believe, right? Yeah. Remember, we computed X sub G and Y sub G in step 4. Okay. And I believe this is actually the only place where we use X sub G and Y sub G. Or actually, no, we used it in other places too. Yeah. Okay. Actually, no, this might be the only place we use it. But of course, if you don't have any thermal generation function, like in part 1 of the project, then you're going to skip this step. Okay. And by extension, if you don't have any thermal generation, then you can skip step 4 as well. Okay. Okay, and so with that, we're done with this loop. Okay, but before we move on to the next iteration of the loop, we have to make sure that we save all the important information that we computed here. Okay. Okay. And so there's three things that we primarily have to save. Okay. Four, excuse me. So first is BG. Okay. And so remember, BG was the value of the physical shape function derivatives at the Gauss point. Okay. One thing that we haven't used yet is the determinant of the Jacobian at this Gauss point, and so we need to save this as well. Okay. And so these two specifically are needed for the element stiffness matrix. Okay. All right, next thing we have to save is our result from step 7. Okay, so our result from step 7 is SG. And so this is thermal generation. Right. Remember, another interpretation of this function is this could be our body force, right? So if we're doing elasticity. And so this would be like the value of gravity at our Gauss point. Okay. And we also need to save n sub g. Okay, remember n sub g, this was kind of fairly early on. So this was step 2, right? And so this was the values of the shape functions themselves at the Gauss points. Okay. And these three things, so including the determinant, this is what's needed for the element forcing vector. Okay. And so of course, if you don't have an element forcing vector, or if you don't have a thermal generation term, then you can go ahead and neglect the last two items in this list. Okay. So when you're first doing your project, you're just doing part 1. You don't have to worry about those last two items. Okay. All right, and so with that, now that we made sure that we saved everything that we need to, you can go ahead and end the loop. Okay, and so we're done. We're done with this part of the done with that part of the loop. Okay, and so of course, just because we end the loop, that means we're going to repeat everything here. So steps 1 through 8, we're going to repeat that for all 4 different Gauss points. Okay, so by the time we reach this point right here, or I should say, by the time we exit the loop, by the time we exit the loop, we'll have all the items in step 8. We'll have all of those items evaluated at all of the Gauss points. Okay. Okay. And so in this kind of initial case, since we're doing it for a 4-node quadrilateral and 4-point Gauss quadrature, we'll have 4 different versions of step A, right? So we'll have four different values of BG, 4 different values of determinant, 4 different values of SG, and 4 different values of NG as well. Okay. All right. Any questions on this? Okay. All right. And so that's the loop part. And so that's a big part of it. But we're not quite done yet because we haven't actually performed the Gauss quadrature yet. Okay. And so step 9, which is outside the loop. Okay. Step 9 is we're going to sum up all the contributions from the Gauss points to compute KE and FE. Okay. All right, question. So determinant of J is part of the stiffness matrix and element forcing? Yes, it's part of both. Yeah, because remember, you're transforming both of those integrals. And so, that determinant of J is going to be there for both. Yeah. Mm-hmm. All right, so first let's look at KE. Okay. And so the way that we're going to compute KE is we're going to take the summation. Okay. Okay. And the summation is going to be from 1 to n. Okay. Or I guess we're summing over G, not little n. Okay. Reflex. Okay. And the way we compute this is we take BG transpose, okay, multiplied by K, not to be confused with KE. So this K right here is thermal conductivity. Okay. In this particular algorithm here, we're assuming K is a constant. But if it wasn't a constant, you would actually have to account for it in the algorithm above. And so you have to compute it at each of the Gauss points. Okay. Then we multiply by BG. We multiply by the determinant of J. And we can't forget our Gauss weights either, right? So this WG here, these are our Gauss weights, okay? For this particular example, since we're doing a 4-point Gauss quadrature, all the Gauss weights are just gonna be 1, right? And so if you recall, if you sum up all 4 points, their weights have to equal to 4. And so each of those weights should be equal to 1, okay? All right, and so this summation here means that we're going to sum over all 4 contributions, right? And so we're going to compute everything in the parentheses here. We're going to compute that for each of the Gauss points, right? Because we saved those variables. And then we just, add them all up, okay? Right, and then FE here is going to have the same, a very similar expression, okay? And so for FE here, we're going to do the summation from G is equal to 1 to N. Okay. And so I've used N quite a bit here. So let me kind of label this N right here. So this NG is what we saved from the loop. Okay, so these are the shape functions. At the Gauss points. Okay. We're going to multiply by SG, determinant of J, G, and WG. Okay. So these are also the Gauss weights. All right. So that's the algorithm. Okay. And so, it's a lot of steps. It seems like very daunting. but you'll be surprised. And so, actually programming this into MATLAB will require less code than you think. And so part one, actually, a lot of the code that you're going to write, I think, has less to do with this algorithm here, and kind of more for more bookkeeping stuff. But that's part one. Okay, part one and part two technically. Right? So this covers part 1 and 2 of project. Okay, and so if you could do this algorithm here, that's already parts 1 and 2, and that's majority of the points right there. Okay, and so that's why I've kind of broken it up into different parts. Okay, because each part by itself, I think, it's a little bit daunting, but you don't need all the parts in order to get a working code. Okay, and so I want you to kind of build this code incrementally. So we're going to start with kind of the bare minimum, which is basically the element stiffness matrices. Okay, then once you can kind of complete that part and you verify that, then we're going to throw in a thermal generation function. Then once you compute that part, then we're going to move on to what I think is the hardest part, which are the Neumann boundary conditions, which we'll go over in just a second. Okay. All right, but are there any questions on this so far? Okay. All right, so so now let's finally talk about how to do the Neumann boundary conditions. Okay. And so, because the Neumann boundary conditions are kind of handled kind of strangely, we usually handle these in a separate part of the code. So, we don't handle it at the same time as what we have up there. Okay. Because the Neumann boundary conditions, they require integration, right? And so that's the last thing we covered last Monday. But these aren't double integrals, right? And so everything that we did so far, for the element stiffness matrix and the thermal generation function, those are double integrals that kind of span the entire element. Okay. The Neumann boundary conditions, the reason we handle them separately is that these are only line integrals that go across, the Neumann boundary. Okay. All right, so if we have kind of a generic element like this, okay. All my generic elements have looked the same today. Okay, and so we have an element like this, and so let's say that this is part of a greater domain boundary, right? And so let's say that this is sitting on a boundary like this, okay? And let's say that this boundary is subjected to an outward heat flux, okay? And so this means that when we go to assemble the element forcing vector for this particular element, we have to add a contribution that relates to a line integral on that edge. Okay, And so this edge right here, we use green. Okay. And so this edge right here, okay. And so we need to perform a line integral on this edge. Okay. To add the contribution from the Neumann boundary condition. Okay. Okay. But handling these line integrals are tricky. Okay. Because if you remember from our discussion about this last Monday, right? These line integrals are only going to be integrals in one dimension. Okay. Right, so we're either going to be integrating in epsilon or we're going to be integrating in eta. Okay, so we're not going to do both. And so whichever dimension that we're not integrating, we have to fix those values. Okay. Okay. And so for a four node quadrilateral, which has four edges, then our Neumann boundary integral can take one of two different forms. Okay. And so the first form is if the Neumann boundary is on either the north edge, the top edge, or the south edge. Okay. And of course, the north edge is corresponding to a fixed value. And so let me call, just to differentiate it as fixed, I'll call that eta naught. And so the north edge is going to have a fixed value of eta naught is equal to 1. Okay. Or if the Neumann boundary is on the south edge, okay. And so on the south edge, the eta, the fixed eta value is going to be -1. Okay. Then in this case, you perform our line integral on the epsilon direction. Okay. Okay. And so our line integral then is going to be summation g equal to 1 to n, okay, of, okay. Let me do this. Instead of n right here, let me just do num points. Because I use big N for shape function, but I want to make sure I keep that variable. Okay. Okay, so this big N right here is shape functions. Okay. And so this is going to be evaluated at the epsilon values at the Gauss point. Okay. But instead of the eta values at the Gauss point, remember we're fixing that value. So we're fixing that value at eta naught. Okay. We need to transpose this just to make sure that it's a column vector. We're going to multiply that by q hat or q bar, and so this is our heat flux value. Okay. Then we have to multiply it by the Jacobian, right? And so since this is 1D, our Jacobian is just a single value. Okay. And so our Jacobian is going to be the length of that side divided by 2. Okay. Then we have our Gauss weights as well. Okay. All right, question. So can I remind you guys how to determine if the heat flux is negative or not? Yeah, sure. And so the heat flux, the sign convention for that is if either the heat flux is going into the domain or out. And so the sign convention is that if the heat flux is going into the domain, and so it's opposite of the normal vector, right? And so we have a normal vector that's outside the domain like that. Okay. And so if the heat flux is coming out of the domain, and so it's aligned with the normal vector, then heat flux is positive. But if the heat flux is going into the domain, okay, then it's going to be negative. So it all depends on how and which direction that the heat flux is aligned with the outward unit normal. Yeah. Okay. All right, and so that's the case when our Neumann boundary condition is on the north edge or the south edge of our element. Okay. And this example here, that's obviously not true, right? And so we have our heat flux on the east edge. Okay. And so the other form that the Neumann boundary integral can take is if our heat flux is either on the east or the west edge. Okay. Okay. And so the east edge, this is going to correspond to a fixed value of epsilon. So we'll call that epsilon naught. Okay. East edge is going to be epsilon naught is equal to 1, or west edge. Okay. So this is epsilon naught equal to -1. Okay. And so in this case, since we're fixing the value of epsilon, then we're going to perform the line integral in the eta direction. Okay. All right, so we have a similar thing, and so we have summation. It's a big ass summation. Okay. Summation of G up to the number of points, okay, times the shape functions. This time we're fixing epsilon, and so eta is going to be our Gauss point. Okay. Everything else is more or less the same. Okay. All right, so those are our two cases for our Neumann boundary condition. Okay, and so for the picture that I drew above, of course we have the Neumann boundary condition on the east face, and so we're going to use the second form of this. Okay. Another thing you have to be careful of here, and this goes for your project as well, is that because these are just 1D integrals, you're not going to use the same Gauss points as above. Okay, and so you're going to use a 1D Gauss rule. And so our 1D Gauss rules, the most common ones are either going to be a 1 point or a 2 point. Okay. And so for a 1 point, you just evaluate everything at the centroid and or the center of the line. And for the 2 point, we have plus or minus 1/√3. Okay. All right. Any questions on the Neumann boundary conditions? I will say that for your projects, the project actually is a little bit more confusing, not in terms of the theory, but just in terms of how do you program it all? Because for the project, you're working with a triangle, and the triangle is not kind of like a square, right? And so you have, for the triangle, you have, even for a right triangle, you have kind of the hypotenuse, you have the the vertical edge and the horizontal edge. I said hypotenuse really weird just now. And so it's going to be a little bit more difficult to determine, which edge that you're going to be on. And I think that's the primary difficulty with doing that. Okay. And so I saved part 3 for last because, determining, which edge of your triangle that you're focusing on and what your Gauss points are going to be, that's going to be the more difficult part. It's not so much the theory, but just it's kind of more of the programming and more of the logic behind it. Okay. Okay, and so that's the algorithm. So that took about just as long as I thought it was going to take because there's a lot going on. And so the next step is that I have an example here which kind of goes through that entire process. Okay, shape function, derivatives, and element stiffness matrices and all. Okay, of course we have 3 more minutes today, and so we're not going to go through with it. But let me go ahead and write down the problem just so that on Wednesday we kind of just hit the ground running with this. Okay. Okay, and so for this case, I have a 4-node quadrilateral. Okay, so it's going to look like a trapezoid here. Okay. So I'll call this node 1, node 2, node 3, node 4. Okay. We have a thermal generation function here, and so our S of x and y, we're going to say this is equal to 20x plus tan y. Okay. Our thermal conductivity here is going to be a constant. And so our thermal conductivity is going to be 10. And the use for that is watts per meter Kelvin. And our heat flux, we're going to have a heat flux here off the top face, the top edge. Okay. And it's going to be coming out of the domain. And so since the heat flux is coming out, our heat flux here is going to have a positive value. So it's going to have a positive value of 5 watts per meter square. Okay. So we'll see all aspects of the algorithm here. Okay. All right. And before we go, let me go ahead and write out the physical coordinates. For all the nodes. Okay. And so node 1 we're going to assume it's located at the origin. So it's going to be at 0, 0. Node 2 is going to be at 1, 0.2. Node 3 is going to be at 0.8, 1. And node 4 is going to be at 0.2, 0.9. Okay. All right, and so this is very typical of what you'll know, for each element in your final project. Okay, so you're going to know what the thermal generation function is if it's there. You're going to know the thermal conductivity, and you're going to know the physical coordinates of all the nodes, right? So x1 through x4, y1 through y4. Okay, and so what we're going to do on Wednesday is that we're going to go through the algorithm. I'm going to illustrate all the steps for you on this particular example using hand calculations. Okay, because I think when you're looking at an algorithm like this, it's pretty dry in terms of what you're supposed to do in each step. And so I think until you kind of put some numbers to it and see it in action, it's a bit hard to kind of know what's going on. So on Wednesday, I'm going to run through the algorithm with you, with this example here for just one of the Gauss points, okay? Just so you can see how everything is done. And hopefully that'll give you some good context for how to start the project, okay? And I think after that, I also have a little bit of information on triangular elements. Just to kind of give you some hints on how to deal with that for the project as well. Okay. All right, any final questions before we wrap it up for today? Okay, all right, so that's all I got planned for today. And so remember, I plan to have your midterms graded by Wednesday. And so if you want to pick up your exam, if you want to come to class on Wednesday, then I'll have those ready. Okay. But if not, I'll hang on to the exam so you can come next week and pick it up as well. All right, so thank you everyone for tuning in today. I know it was kind of a lot today. I've been kind of saying that a lot lately, but you know, the end is in sight. And so we have one more lecture of content, and then we're just gonna be working on the project from there. Right. So thank you everybody. Hope you guys enjoy the rest of your evening, and I'll see you guys on Wednesday. Thanks. Have a good night. Yep. Sure. Yeah. Okay. Yes, yeah. So for the project, we're going to use a 3-point Gauss Rule, and it's going to be those things. So, so you just need to code those in. And so the way I kind of structured it is I put it into a matrix just to make it convenient for. And so I'll kind of show you how to. Okay. Yeah, and so we defined the size of it. So, so we're going to need 6 lines of code. So let's do GP. Yeah, so GP. Well, let's put them in the matrix. Let's go to GP. That'll be the very first one.
Sounds like all this. I just wanted to see that.
Yeah. 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 Yep. Okay.
I don't know what's on that.
Yeah, that's fine.
And then put this in matrix.
Yep. 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 No, I don't think you need that. So part one of the code. Oh, so these are shape function group. Okay, yeah. So this is inverse times. Yeah. That's good.
And then this part.
Yeah. So and so for this part, actually you don't need the Gauss matrix. First part of it, actually. And so right. So what you're going to do is you're going to perform basically step 9. So that's going to be this one. So this right here. And so what you're going to do is you're going to take and so let's do this part of it. Yeah. So you transpose that. So you want to take just a pause. Maybe put it in parentheses. I'm always paranoid.
Yeah.
You're multiplied by the same thing again. Yeah. Multiply this. I think the weights for the 3-point rule is just 1. So we must, oh, you need to multiply by the determinant. You need to multiply by the determinant. Yep, there you go. That's your own 6. I guess you don't need the Gauss Points. All the derivatives are just constants. Okay, yeah, so that's good. Yeah, I remember that. I remember that doing the project last year. When someone asked me, it's like, why do you need the Gauss Points for this part? I guess you don't. For the quad, you need it because when you do these ones up here, those for the quad, you have that one. But for the triangles, they're all different. So you actually don't need that. Not until part 2. Yeah, that's good. So I think now you just have to assemble.
It's like, sure.
Yeah, so for remember you're assembling, you're not assembling it 2 by 2. Each element is 3 by 3. So you need to kind of account for that as well. And so you're also going to need to do IND1. So IND 1, 2, 3. So if you actually the good place to check for this is actually going to be our first method, the frame of the truss. Because IND 1, IND 2, IND 3. Not only does this tell you the node number, but this tells you what row in the matrix that the matrix is. And so you need to incorporate that. So I would look at kind of our task code in trusses, or the truss code and the frame code. To kind of give you something. It's very similar. The only difference is that for this one, it's a 3 by 3 and stiffness instead of a 4 by 4. And so it's short. But the idea is the same. So you compute the indices using the ID, the connectivity matrix, and then use that to put the stiffness matrix. So actually, use one now. She's so this part right here. And so we computed the IDs, and we actually use the connectivity matrix in here, and so you don't have to do this one here. But everything down here is very much the same. Direct reference. Except now our element stiffness matrix is 3 by 3. 1, 1, 1, 2, 1, 3, then 2, 1, 2, 2, 2, 3, 3, 1, 2, 2. But the object is exactly the same. Yes. Yes. Yep. No, the global one is going to determine how many nodes that you have. And so if it depends on your mesh. So if your mesh, let's say, has like 500 nodes, then it's going to be 500. Yeah, it could be 300 somewhere. Yeah, so good start. Yeah, so I think this part should all be correct. I'm just looking at it right now. And so I think once you get the assembly and the membership, for the tertiary boundary condition, so actually the final project code shares almost more so than one. I think the only one that's the only part that would take from one but everything else we kind of take from this. So kind of have both codes as reference. So we did. You don't have to do it yes, but if you want to get a head start on part 2, then you have to fill in. So there's 6 entries in this matrix. So that's going to correspond to the 6 steps. So you won't have to notes again. The course notes or the lecture. It'll be, let me scroll down. It'll be this 6. So this is basically your 3 by 2. Yeah. So you have to mark it. So GP 1, GP 1, 2 is going to be 6. And then so you don't need it for part 1, but part 2 you're going to need it because that's yeah. Let me check on Zoom first. I'll come back to you. I think someone asked a question. Right. Someone asked a question on Zoom. Oh yeah, sure, Aaron. What's up?
Hi, Dr. Tran. Quick question for you. Not EGME 541 related. I was just confirming to see if you got my email regarding my project defense report.
Oh, yes, I believe I did. Yeah, I'm a little bit behind on emails, but I think I saw an email about it today. Yeah.
Awesome. No worries. Just checking.
Okay, yeah, if I didn't, I'll follow up with you, but I'm pretty sure I got it.
Great. Thanks so much. Appreciate it.
Yep. All right, good night.
Have a good evening. Thank you.
Yep.